Okay, so let's go a bit further. So first we are here, and the first point here is something we've already said. To obtain a basis of the column space, simply keep the columns of A corresponding to the pivot columns in the echelon matrix. Okay, so that's actually very simple. Then let's see. We're going to define the rank of a matrix. I don't know, I don't remember if you worked on that last year, but anyway, that's going to be a very important concept this year. The rank, it's actually the number of independent columns, all right? So that's all. That's as simple as that. But what does it mean? As we said, these independent columns were going to be a basis for my column space. It's also the dimension of the column space, okay? And sometimes you will see that called the rank theorem, all right? Not, never mind, okay? The thing is that what is important here is that we have seen in the examples, and well, we could prove it more generally using these kind of things, all right, that the number of independent columns will be equal to the number of independent rows. Okay, so number of independent columns, and what is we said that this matrix was the reduced row echelon form, so it also corresponds to the best linear combinations you could do in order to get towards the identity. So that also denotes the non-zero rows are going to be the number of independent rows. So and the thing is that you remember how we created this. So let me erase a bit that. We created those C and R matrix. When we were creating the R matrix, we will have, okay, every time we find a dependent column like this one, it will never have coefficients below the previous pivot. Okay, it will never have non-zero coefficients below the previous pivots, because we are really trying to say, well, this last column here actually depends on the first two ones, so it must be a combination of those two numbers. So that's what we were trying to say. So that means that you will have as many pivots as you have independent columns. Okay, as many pivots as you have independent columns. So that's something actually quite huge. The number of independent rows is really equal to the number of independent columns. You can see that maybe work. See how many independent rows you get in that one. Okay, that's an interesting exercise too. All right, and so you will get you've got two independent rows. Well, we obviously got it because when we did the radius row echelon form, that this is what we obtained, only two rows with a pivot. Okay, so all right, so let's see what comes next. We've got this formal definition that the rank of A is equal to the dimension of the column space of A, okay? And so something that we can say, so we've just seen that as a rank of a matrix, but we can also talk about the rank of a family of vectors, and it's just going to be the dimension of the space spanned by these vectors. And in order to find that, you can create the matrix with all those vectors as columns. All right. Okay, and we obtain this theorem. Given a matrix A, its rank is equal to the number of independent columns, which is equal to the number of independent rows, which is equal to the number of pivots in the echelon form of A. Okay, so when you're doing the echelon form of A, you can just simply count the number of pivots, and that's giving you the rank of the matrix. And you can also get those pivots to spot the columns which are independent, and that's going to give you a basis of the column space. Okay, so that was our first fundamental space, vector space related to some matrix. Next one is going to be what is called the null space. Another name for the null space is going to be kernel. Okay, that's I think well, I know that in France we only use kernel, and in the Anglo-Saxon literature they use null space for matrices most of the time, and kernel is for more general linear maps. Okay, but whatever. Okay, we're good. Let's stick with the null space denomination for during this part of the semester, and when we will go to kernel, don't forget it's the same idea. What is that? Okay, the null space is just going to be the set of any x in the domain of our matrix when we consider it as a function, such that it gives you 0. Okay, so that means your matrix has n lines and p columns, so that's your matrix A with n rows and p columns. And what can you apply it on? You can apply it on some x's that belong to, well, it has to have as many rows as A has columns, so that belongs to Rp. Okay, and so obviously the null space is going to be a subset of Rp. Okay, that's the first thing that is very important, and it's going to be the set of all items such that it is equal to 0. Okay, all items such that this multiplication is equal to 0, 0, 0, the 0 element of Rn. Okay, not any 0, the 0 element of the image, right? uh, that belongs to the column space, right? So the column space, let's sum up something that should be very clear. The column space was a space, a subspace in Rn, while the null space is going to be some subspace in Rp. Okay? All right. Okay, so maybe before we go any further, let's work again on our previous example. So we had 1, 2, 3, 4, 5, 6, and I had 3, 3, 3. Okay. Okay, well, that's a square matrix, but anyway, that's still interesting. So how do you find the null space? Well, basically, what you're going to do is you want to solve this equation. Okay, that's pretty simple. And what are you doing to solve this equation? Well, you have several ways to do that. Either you work with the 3 lines, well, we've already talked about that. So either you work with a system like x plus 4y, so that's a z, plus 3z is equal to 0 on 2x plus 5y, etc. Or you work on the augmented system. Well, do you really need augmented? Answer is no, because any combination you will do between any linear combination you will do with 0 is just going to remain 0. So what are you doing? You're just working on your matrix and get it as a reduced row echelon form. So again, we're looking for the OR matrix. So what was our OR matrix? It was 1, 0, 0, 1, negative 1, 1. Okay, and then what you want to find now, it's very easy to find the xyz such that this is equal to 0. Remember, you've got your free variables, the one that don't correspond to the pivots and the pivots. Okay, so pivots, dependent variables. So the dependent variables are going to be the x and y's, and the free variable is going to be the t. So what are all the solutions to this equation? So free variable, put z is equal to t. Then we get y is equal to minus z, so which is equal to negative t, and x is equal to plus z, so plus t. So in the end, what have we found? We have found that the set of solutions to that equation would be anything written like t, negative t, and t for any t in R. Okay? How would you write it with a span notation? Got that? So that would be, well, one way to one intermediate notation would be I can write this as t times 1 negative 1 1, again for any t that belongs to R. And another way to say that is to say I want the span of the vector 1 negative 1 1. Well, that's the single vector. Okay, and this is going to be my null space. Okay, this is the set of all the solutions to equation ax is equal axyz is equal to 0, 0, 0. Okay, all right, so that was an example. Let's go back to what's written here. So we want to find the null space by solving equation x equal to 0, and as you know, you should put A in a reduced row echelon form in order to perform this. Then, once you're in the reduced row echelon form, you've got the leading variables and the free variables, okay? And what's that going to be? And so using the free variables, you can create your set of solutions, and according to the number of free variables, it's going to depend on one or two or more parameters. That is going to be the dimension of your null space, okay? And that dimension, sorry about this, that dimension has a very nice name. It's called the nullity, okay? Well, although I've only heard the word nullity in the coming theorem, which is called the rank nullity theorem.